So, as I said earlier, I am a postdoctoral fellow in computer science at the University of Leuven, and I will be talking about deep learning for fashion attributes. Sorry. So this is joint work with Juan Carlos Gomez, Sean Moons, Gert Heyman, and Katrien Leijnen. I gratefully acknowledge their collaboration. So what is the goal that we had for this work? So basically, we proposed the problem as a translation problem in which we wanted to translate images into text and vice versa. So given an image, we wanted to have text that describes what's in the image. And given some text, we wanted to find images that actually display the attributes on the text. And we do this without relying on the querying modality. So this is a cross-modal task. And we don't want to have any annotations in the image when we go from text to image, for example. So we don't want to rely on tags that have already been on the image. So basically, we really want to do it in a cross-modal way. So we want to design algorithms that can bidirectional translate between these two modalities. And this is an important task for me personally, because I think this is, to do this, it's a token of human intelligence. So humans have this ability to, you see an image and you can describe into words what's in the image. And you can go vice versa. You see a text and you can visually imagine what that text looks like. So it is really a human trait. And so I find it actually quite interesting to go back and forth between things that can be just instantiated in different modalities. Beyond that, of course, beyond the scientific interest, there's also some business benefits that I'm sure by now you have all heard, and you will keep hearing, I'm sure, throughout the summit, that if you can translate images into text, you can automate, obviously, image annotation. You can also simplify search, because you don't need to rely on actually tagging your images. You can just have the user input some text. And without having tags on your images, you can actually find things that are relevant. And obviously, you can also go or identify what your customers are interested in with more fine-grained attributes if you understand both the images and the text, improved product recommendations, and then obviously help customers find similar products. Sorry. So these are some of the research questions that we posed. First, how will we represent these multimodal documents? So we had images and text. How do we represent them together and not just each of them separately? And we also wanted to do this in a more realistic setting in which we actually wanted to learn from data that is ubiquitously available on the web. So on the web, most of the data is not cleanly annotated. Most of the images are, you have lots of e-commerce websites, and they have these product descriptions written in natural language, but they're not, most of the time, not cleanly annotated. And if you compare between different e-commerce sites, they would have different tags, perhaps different product descriptions. So we wanted to do this. We wanted to learn from data as found on the web. We wanted to also learn completely unsupervised. And this is a bit different from a lot of the computer vision tasks that are out there that actually heavily rely on cleanly annotated data. And we also, of course, so as I said, we didn't want to rely on expensive human annotations. We also didn't want to put our knowledge into it. We didn't want to have prior knowledge. And we also didn't want to have dictionaries. Nobody had to sit down and say this feature corresponds to this particular piece of text. And finally, how do we cope with the noise in the data? So it was a challenging problem given how we framed it. I guess, this is just to illustrate a little bit on the image side. We worked in particular with garments, but even if the scope is narrowed, So we didn't, for this particular task, we didn't work with a whole broad range of products. It was mostly dress-like garments. But even within there, there's a lot of variation. There's a lot of visual variation in texture, in patterns, in colors, in shapes. So we kind of narrowed that. And on the textual content here, I just put some tags that we're interested in perhaps finding out. But our data actually looks like this. So we have the image, and you have a lot of text in natural language. And this is, we crawled this data set from Amazon. Most of the time, there are people trying to sell things on Amazon, and they write their own, they write their own descriptions. And as you can see, they're actually quite noisy. Here, we have some words, the ones in green, for example. They're actually described in the image, but there's also a lot of text there that has nothing to do with the image. So we had to basically learn how to deal with these things. While we focus on images having clean backgrounds and we focus on the fashion domain, as I said, there's still large variations in the visual side, but the text is also extremely noisy. So there are false positives. So by false positives, I mean words that appear on the description may be wrong. So at the end, you have also available in white, red, and blue. So if we're trying to use this as training data, it can be very confusing for the model if your tags are actually off. So these are the type of things that we had to deal with. And also false negatives, because not everything in the image is mentioned on the text. So it's quite incomplete. And as I said, this is not highly curated data. So, but the main idea that we had was that because we have e-commerce sites and people just freely write what they want, we could just leverage this information. So basically, we had thousands of pairs of images and textual descriptions. And our key idea was like, OK, so let's just try to learn from this natural alignment between the images and the text. So here I'm just, I will not go into every method that we tried. I'm just kind of listing them there, just to give you an idea of the things that we tried, and then I will kind of summarize. So on the textual representations, we tried two approaches. We tried a bag of words, just meaning we just count for every word, we count how many times every word occurs. So this is a very straightforward approach. But we tried two vocabularies. So basically, the problem that we had was that it was difficult from the text side to actually know what are the words that are actually descriptive of the images. So we tried two approaches. One approach was based on a part of speech tagging. So meaning we recognize whether each word is a noun, a verb, or an adjective, and just keep those and then disregard everything else. You can imagine that's still quite noisy because obviously not every noun is actually describing, but some nouns are describing the images. And we also used an external vocabulary from Zappos.com, just because they're a large retail, and we figured, OK, if they are using that vocabulary, that can be actually useful for us as well. So we kind of also tried just filtering out everything except the vocabulary that Zappos uses to categorize their products. We also experimented on the text side with word embeddings. I think by now you have heard lots about word embeddings and their power. So we used Word2Vec. We used it both trained on a large news corpus and actually trained on our text. And this actually led to the best results when we actually trained on the fashion domain. So we actually learned word embeddings that are capturing both the semantic and syntactic relationships between the words in the fashion domain. So that was on the textual side. On the image representation, we actually tried the scale invariant feature transform, SIFT. That's old school now. But we tried it, just to see. And of course, we tried convolutional neural networks. And then we tried different aligner models. And in particular, we tried bilingual latent Dirichlet allocation, or BLDA for short, canonical correlation analysis, and a neural network. So I will go a little bit deeper into some of these. So from the image representation, I think by now you have already seen many, many times convolutional neural nets. So we, as a first approach, we just had an image pre-trained on ImageNet. We fed it through a convolutional neural net and just used the weights or the vector that this pre-trained network had. We just used it as a representation of the image. So nothing fancy there. So on the alignment model, this is the bilingual Dirichlet allocation. And this is actually a Bayesian network that is used quite often, or before convolution, or before the revolution of deep learning. This model was actually used quite a bit to translate texts between languages. And so the way we approached it was because we wanted to translate images to text, we thought, okay, let's try a translation model. And the way we do it is that we think that every pair of image and text, we think that both the image and the text were generated by a common topic distribution. So we assume that a topic is like a cross-model structure that can be instantiated either as a text or as an image. And you can then see that given a topic, you can generate words in the visual domain, or you can generate words in the textual domain. And what do I mean by words in the visual domain? Well, it turns out because convolutional neural networks are so powerful, you can interpret the vector of the convolutional neural net as a sort of vocabulary. So each index in the convolutional neural net can be interpreted as a word ID. And then the value of it, you could interpret it as the number of times this word ID occurs. It's a little bit of an interpretation of the convolutional neural nets, because at the end of the day, a convolutional neural net is just a set of features. And you can interpret these features as IDs of something, of a concept. So then we had these models that could deal with words, but it wasn't so clear, okay, what is a word in the visual domain? And this has been done with SIFT features quite a bit, that a lot of the textual representations were used to work with visual words using SIFT. And here we used it with convolutional neural nets, and it's actually not bad, the results that we got. So, well, for learning, I'm not going to go into all the math, but basically we're learning, given a pair of image and text, we learn a topic distribution. And then given some topics, we learn how to generate either visual words or textual words. At inference time, we have a new image, and we try to then infer the topic distribution of that image. Or we have a new text, and we try to infer the topic distribution of that text. And finally, at retrieval time, we just marginalize over the number of topics, and then we can go back and forth. So given a new image, we can generate words, or given some text, we can find the most similar images. And this is just by similarity or by marginalization. All right. So the next alignment model that we tried was a neural network. So here, what we did was we fragmented the image into boxes. And each of these boxes, we put it through, again, a pre-trained convolutional neural net. On the other hand, we had words. I don't know where the pointer is. But yeah, on the other hand, we had words. And these words were represented as a word2vec. So we had already trained our word2vec. So we already knew how to translate the words into these real-valued vector spaces. And given that we had that, what we wanted to do was to create an objective function that would encourage, if you had an image and a word that occur together, you want to encourage that the dot product between those two vectors is high. And if they didn't occur together, you want the dot product to be low. So basically, that's what I'm showing here. This is the dot product between the word representation and the image representation. And we want to learn basically the weights. So here, the convolution neural net gives us a set of weights from the original pre-trained image net. But we then project that representation into a multimodal space where we can both project the image fragments and the text. And we have an objective function that has, well, 3 parts: the fragment alignment, the global alignment, and then the regularizer. I don't go into the details, but there is a paper coming that actually describes in detail exactly how we did this. So basically, just as an intuition, let me just speak really quickly, yes. Okay, yeah. Just as an intuition, the fragment alignment tries to encourage that the fragments in the image are consistent with text snippets that appear on the text side, or 2 words. The global alignment wants to ensure that, in average, the whole image and the whole text are actually aligned. So we have an alignment on different scales somehow, or different granularity. And finally, we have a regularizer just to make sure that the weights are, the norm of the weights are kept in check. And then we did some experiments. So today, it seems like just 48,000 images for training is actually quite low. But this is what we had at the time. So we had to train around 48,000 images, so text and image pairs. Then we learned this multimodal space with these different alignment models that I described. So the bilingual latent Dirichlet allocation, the canonical correlation analysis, which I did not go in details here, but you can see it in the paper, and the neural network. Then, of course, we do the classical cross-validation to find the hyperparameters, and we had 4,000 pairs for that. And finally, we test on 1,000 images. And the way we test is we perform image annotation and image search. So because we had the actual text, we could see, okay, how well can we predict the text that is in the image, and then the other way around. If we had some text, can we find the image that actually had that particular text? And then we compute precision and recall. So these are some representative results, just to show you what we obtained. So basically, oh, something went wrong there. So basically, the BLDA model performed actually really well on the image annotation task, and really poorly on the image search task. And conversely, the the neural network performed really well, or much better than the other models, on the image search task, and really poorly on the image annotation. And so here you can, oops, well, yeah, it's fine. Here you can see, yeah, the BLDA was, these are basically the results for image annotation and image search. And the reason we think this happens, this a little bit counterintuitive that perhaps, yeah, a model turns out to be better for one setting and not so well for the other setting. It's just the way the BLDA and the neural network actually work. So the BLDA is actually really good at generating words. So you can see for the image annotation that BLDA is actually capturing more of the semantics of what is happening. But to generate images, it's not so good. So it can generate visual words, but a visual word is not necessarily an image. So in that case, the BLDA didn't perform so well, whereas the neural net performed better. These are some qualitative examples. Like we have an image of some dresses. These are images that, these are test images. So these are images that our system did not see before. And we can predict things that are actually in the image, like sweetheart and strapless and things like that. I'm not going to go into every example, but just to give you an idea. And this is the image search, or the text to image. So here we had a query, little black dress, polyester jersey lace. And it actually finds things that are quite relevant. So yeah, just bear in mind that this is actually going from text directly to images. So it's really a translation mechanism. There's no text around the images. So yeah, just a couple more examples. Yeah, here you have casual sleeves, floral print. These are the things that are found: long cocktail, wedding gown, strapless, yellow. So it does capture what is in the... And we just have a couple of online demos that I want to show. I think I'm out of time. Yes, I actually don't know. Oh, yes, thank you. Just really quickly, and then I conclude. This was our, I mean, here I just want to show you again. This was what the training data looked like. I mean, we had pairs of these, images, but this was our labels. Like, this was quite noisy. So you can see there's a lot of stuff. There's a lot of noise, a lot of incompleteness, a lot of incorrect tags. And so we were actually quite surprised that we could learn anything. Here is just, we have a text-to-image demo. And perhaps you're looking for something red. It's not perfect, but roughly there's lots of red. And then again, like, there's no annotation in the image. So it just goes through a translation mechanism. If you want something floral, it's florally. Again, not perfect, but we're actually quite surprised that these things actually worked at all. And ruffles, these are quite ruffly. So, and then for the image to text, we're actually offering this as it will be offered as an API. So if you're a small company and you don't want to deal with all the machine learning stuff, and you kind of want to outsource it, so we're offering this service as an API. And this is more classical machine learning, where you just have an image, and then you just find attributes that describe the image. So short sleeves, floral, round neck, top dress, things like that. So yeah, feel free to try it out. It's still in beta, but here it detects colors. It detects that it's short, it's a dress, it has short sleeves. The neck perhaps not so much, and this is certainly not the case. But yeah, it can detect also other objects. So that's the demo I have for you. You can also upload your own images or your own URL. This is at requidis.com. We'd love to see if people are actually interested in using these things. And if you could just, I guess I'll just wrap up. So conclusions. So we did a cross-modal search in the fashion domain. We went from images to text and from text to images. And we developed these novel representations for the task. We achieved state-of-the-art results. And then we are providing this image annotation service that hopefully will be used for some people. Any questions?